Welcome to Lecture 9 on Lagrangian mechanics. So here I'm taking a little detour from Carroll's book. Well, I mean, he has some of this, but I'm going to expand a bit and just tell you a little bit of my own thinking on these things. So I just want to take a few minutes to discuss what's called variational calculus. Basically, the problem of variational calculus is to find a function which optimizes a given functional j with respect to some family of appropriate functions. Typically, this involves integrating a Lagrangian. So, as a toy example to kind of sort through these ideas, let's look at a functional j which is based on y, and you've got some Lagrangian here f, which is a function of y, y prime, and x. This is pretty typical. Of course, you could consider in principle functions of more than just the variable and its derivative. You could look at like higher order things, but oftentimes applications just look at the variable and its derivative. Now, here y is taken from some family of functions, in this case differentiable functions, whose graphs contain x1, y1, and x2, y2. All right. Now, so if y star is an element of that family, and we introduce another function eta, which vanishes at the endpoints, then we may study a whole family of functions in this family of functions. So a subfamily, I suppose, which again also go through x1, y1, and x2, y2, right? And we can, using this eta, we can build a parametric family, y of x comma alpha. So we take our, I'm going to call y star y of x 0, x comma 0. So alpha equal to 0 will be the given star one, and alpha times eta, that gives you a function who's also going through the graph. Right. So here's kind of a picture. See if my picture's on there. Yeah. So you've got, fixed endpoints, you've got your given y star, and you can add a variation to that path, which the variation in this case would be alpha eta, like that. Alpha is a real parameter. Okay, so then we can restrict the functional to just this particular class of paths, right? We can look at j of alpha, which is going to be f of, functions in this alpha family, the derivatives, and x. Now, here's a claim, and this is, I think it's a reasonable claim. If y star is an optimal path for the functional j, then we should expect that partial j partial alpha equals to 0, right? So if y star is an optimal path here, then it stands to reason that if you restrict to just looking at this parametric family that's close to y star, then surely it's also optimal with respect to the family, right? But the difference between like the arbitrary set of all possible paths from, say, here to here and this family is, well, the family parameterized by alpha, right? Whereas just the set of all paths, well, you couldn't just use a real parameter to describe all possible paths, differential paths from these 2 points, right? But if you fix your attention on this one parametric family, then you can use real calculus to kind of say what goes on there. And so let's study that then. Like, what is that? What happens there? So, all right. So we keep in mind the alpha parameterized by alpha family. We're varying it according to this eta, which vanishes at the endpoints. The derivative goes like that. Alpha is just a real parameter here. It doesn't differentiate really. And so if you look at this, partial y partial alpha is equal to eta from over there, and then partial y partial alpha, partial y prime partial alpha would be eta prime, which would be, of course, d eta dx. And so we're going to assume also that our class of functions is nice enough, and that the Lagrangian is nice enough, so that the the derivative, the partial derivative of the integral is the integral of the partial derivatives. That condition can be met if we assume certain bounding properties on the Lagrangian or something like that. If it's got a certain uniformity to the continuity of the function, we can do this switching of integration and partial differentiation. Standard, there are standard theorems and analysis for that. And then, okay, so then, since this is a function of 3 variables, we get a chain rule like so, and we get that, right? And then, okay, so then, let me scooch this up a bit here. And then, all right, so then I have, now there is no alpha dependence on x, so that's just 0. And I've got an appropriately colored marker. I'll use a orange one to do that one there. 0. There we go. And then, okay, so we've got, on the other hand, remember partial y partial alpha was eta, partial y prime partial alpha was d eta dx. And then we do integration by parts, which is really the product rule, right? Identity. So we trade this product of derivatives for the derivative of the product of partial f partial y prime and eta minus the derivative of the first one times the second one, like that, right? That's basically, that's the integration by parts. But it is the product rule identity, right? And okay, then what? Well, then notice that that gives us 2 pieces, the integral of the total derivative and then this piece over here. But the integral of the total derivative by fundamental theorem of calculus gives us back, this guy is the antiderivative, of course, and when you plug in x1 and x2, you get eta of x1 or eta of x2 on each term, and those are separately vanishing by assumption, and so that's 0. And on the other hand, you get you get this term here, right? But we're assuming that alpha equal to 0 corresponds to an alpha optimal path, and since this has to be equal to 0, for each, the only way that this can be 0, the only way that this whole thing can be 0, right, if you start thinking about it, since eta was arbitrary, it follows that we need the Lagrange equations to hold for the path, which optimizes the functional j of y. So the Lagrange equations are precisely that this term we found right here vanishes. So partial f partial y minus d dx of partial f partial y prime equal to 0. These are the Lagrange equations for this toy model. Now, this is not how physicists typically write these things. Let me show you how physicists typically write these things. Physicists tend to write things in terms of the variational, like just the variation of the action. And so they talk about it in terms of taking the variation. So del j is the variation of this, but the integral of the variation is the variation of the integral is the integral of the variation. And then there's a chain rule for variational derivatives. It looks like this. And then, but variation of x is 0, right? And the variation of y prime is this, but you can commute the delta and the ddx because that's how it works. So they'd say something like that. Delta x is 0, so we get this. And then, of course, we can trade by the product rule. We can rewrite this as these 2 terms, which you recognize this is the integration by parts step again. But then we've got this is a total derivative, which we get this because the variation is assumed to be vanishing at the endpoints, so this is 0, and you get this, which is, of course, well, that's exactly the Lagrange, if we set that equal to 0 equation. And since the variation of j was 0 for arbitrary variations, delta y, we find once again the Lagrange equation. So this is what I saw, basically, in my junior level mechanics course. I never had a course in variational calculus or anything like that. And this is how variational calculus first appeared to me as a physics student. And I was deeply unsatisfied with it because I couldn't understand why. Why would this be true? I had no earthly idea, right? And so later, much later, for me, when I was teaching advanced calculus, I found these ideas. I don't remember where I found them. Maybe Arfken and Weber. a mathematical physics, popular mathematical physics book. And anyway, if you start looking in the variational calculus books, you'll find things like this. And of course, if you look into a book of variational calculus, you'll find much more. There's all kinds of analysis. I'm soft pedaling here right now. Variational calculus is typically a graduate course. It's a pretty deep analysis course. The interesting thing is these problems of variational calculus, they used to be part of the mainline calculus course. If you look at calculus texts from the early, say, 19th century, you'll find that there was a chapter on variational calculus at the end. See, because these problems of variational calculus were important problems that motivated the study of calculus for scientists, mathematicians, and so the problems of variational calculus were with us from the start, and for various reasons they've just fallen out of the popular venue. I mean, I don't know anybody who teaches a week on variational calculus in the third semester of calculus here or anywhere really. Formally speaking, there's really nothing stopping you from doing it mechanically. Pragmatically speaking, to really push past the Lagrange equations and get more past that, you do need some differential equations. That's probably one of the main things that's keeping that from being an undergraduate course. Is like you kind of need differential equations before you can really hack through a lot of these things. But it's unfortunate because it's a powerful method, and it lies at the heart of how we understand physics today. Variational calculus is important. And there have been very, very sophisticated, revisions of variational calculus from base principles in the past 50 years, 30 years, I guess. I don't know, 40 maybe. There's some very deep, deep books written on these things. I wish I could remember the name of the author. Oh well. So Lagrangian mechanics is mechanics done from using variational calculus, all right? And so here the difference is we're not just going to have one y, we're going to have n functions we're trying to find, all right? So, and a functional is a function of functions, so it's something that's a function of infinitely many variables. And but anyway, so you've got n functions you're looking for, and you think about these as being sort of generalized coordinates for some physical system, and then you look at their derivatives. So if you take the space which has the generalized coordinates and their derivatives, this is sometimes called phase space, or in mathematics perhaps you'd call it the first jet space. And anyway, we let T be the kinetic energy, and we let U be the potential energy of the system. Then the Lagrangian, L is T minus U, and the action is the integral of the Lagrangian. Taking the variation of the action and supposing that the variation is 0 is called Hamilton's principle of least action. In other words, nature is lazy, and so the variations of y1 through yn are independent, and in the sense that each one of them gives a separate Euler-Lagrange equations. So for the same calculus that we just went through, either formally or more carefully with my alpha stuff, you can get from a big old chain rule, you get applying the integration by parts for each variable really separately. You get Lagrange equations like this, one for each variable. And so we have not one Euler-Lagrange equation, but what is this here? This is the work of a Benjamin. Interesting. Well, at least this note was not, this could have been bad. This could have been bad. This wasn't too bad. My 5-year-old only did this much to this note. That's good. That's good. Let's count our blessings. So we have Euler-Lagrange equations 1, 2, all the way out to n, a fold of them. And by the way, one of the things that might catch you off guard here is that we are treating y and its derivative as independent variables. Now, that kind of begs the question, wait a minute, don't you just differentiate this to get to that? And if so, aren't they dependent? Well, you must suspend your belief that this is connected to that through differentiation. We're just treating them as formal variables for the calculation here, all right? Which is a lowbrow way of saying these are calculations on first jet space. They're not really calculations down on the base space, whatever that means. What I'm trying to tell you is there are ways of formalizing that independence, and it does lead to interesting mathematics. All right. If you want to read more about phase space and stuff like that, I think the book by Teitelbaum's got those things in it, or Jose and Salaton's Classical Mechanics. There are more recent classical mechanics that really take a more, what's the word, rigorous look at phase space and what that all means. Not really the point of this course, so I'm going to kind of go on here, but with an example. So if we have a free particle in 3 dimensions with mass m, the Lagrangian's just this, because that's this mv squared. That's kinetic energy. And so you calculate the partial derivatives with respect to x dot, y dot, z dot. You get the 2, you just get 2x dot times m over 2, which just gives you mx dot, my dot, mz dot, respectively. Notice that that's the momentum in the x direction. That's the momentum in the y direction. That's the momentum in the z direction. That's not an accident. Generically speaking, if you take the Lagrangian and you differentiate with respect to q dot, you get the generalized momentum in the qj, of qj, whatever it is. So for linear coordinates, it just gives you linear momentum, like this. And of course then the Lagrange equations are just Newton's second law for the x and y and z coordinates. And well, this one I can solve. We just get lines, right? Which is to say, I think that's Newton's, which is it? Newton's first law, an object at rest tends to stay at rest, or in rectilinear motion unless acted upon by a outside force. I'm paraphrasing here. But, this is part of that, right? Integrate the acceleration twice, you get a line. Or if the v's are all 0, you get at rest, right? So, yeah. So there's that example. No potential energy for that one. You may not have ever seen a spring like this, but if you could imagine a 3-dimensional spring anchored at the origin, all right, so it's like, imagine the spring at the origin, and it can go in each direction out from the origin, right? And so that spring is somehow mounted on some kind of, mount that can go any which way and has no friction. It's able to pivot anyway. Don't ask me how to set this up. Just imagine that you could. And then how much the spring is compressed or stretching will depend on just the distance to the origin. And so a way to write that would just be the force is minus kr. So let's see here. Well, anyway, so that would give me minus kx, minus ky, minus kz. And so if I look at that, that's the gradient of minus the gradient of 1/2 k times x squared plus y squared plus z squared. So if the gradient of this gives me that makes it the potential energy, right? Because the force is equal to minus the gradient of the potential energy. And anyway, so the Lagrangian is 1/2 x dot squared, y dot squared plus z dot squared. That's the kinetic energy minus the potential energy. And when you calculate the Lagrange equations, here they are. So, it's kind of neat. I think you could solve these. They're just, it'll give you sines and cosines in x, y, and z. So it would be like a, sort of like a 3-dimensional harmonic oscillator kind of thing. I didn't actually write out the equations for it. Oops, did I get everything on that last page? Sorry. I think I did. Yeah, I think we got it. All right, so continuing, really not much, I'm not really saying much, I'm just cleaning it up a bit. So what we had there was these equations are the Lagrange equations, but by the way, they're also precisely Newton's second law in this case, and also in example 1, they were also Newton's second law, because the reason for that is that the coordinates were just linear coordinates. They're just regular Cartesian coordinates. So in the case of Cartesian coordinates, it can be the case that the Euler-Lagrange equations are exactly just Newton's second law, all right? But in general, there's something different. So like this one, example 3. And it doesn't have to be anything terribly abstract. All you got to do is just not use linear coordinates. Just don't use Cartesian coordinates when you do that. the Euler-Lagrange equations automatically pick up the slack. You don't have to state things in terms of rectilinear coordinates for Euler-Lagrange approach, which is the beauty of the method and why every physics major should be required to understand these things pretty deeply. Because it's a toolbox, we can solve a large set of problems that introductory physics can't touch. So like here's one. You have a mass m, potential energy is a function of r, the radius in 2 dimensions, and you're using polar coordinates r and theta. So in that case, you can work out that the formula for the speed squared is the radial speed squared plus the tangential speed squared, but the tangential speed is r times omega in the usual language, but that's r theta dot, so this is just the tangential speed squared. So there's the formula for like speed in polar coordinates, and then I said you've got a potential energy, which is just a function of r. So when you calculate partial L partial theta, it's 0, and so that gives us that ddt of partial L partial theta dot must be 0. But what is this? Well, that is mr squared. You might recognize as the moment of inertia about the origin for a particle of mass m, and of course that's angular velocity. So this is I omega in the usual parlance of introductory physics, and this is the conservation of angular momentum for the system. The radial equation is probably less familiar, and here it is. Partial L partial r is equal to ddt of partial L partial r dot, which gives me this. So yeah, mr theta dot squared minus du dr equals to mr double dot. I think if I was to, you could think of this as like a sort of a force. So this would be the radial force, right? And this, if you rewrite it, you could write this as like mv squared over r, where v is the tangential speed. And so you could think of this as being a sort of centrifugal force. You know, this you could think of as a fictitious force, quote unquote. And just notice how the Euler-Lagrange equation just naturally builds in that term, which is a frame effect of the fact that we're not using just Cartesian coordinates, right? We're using a mixture of one linear coordinate r and the theta. But anyway, so there's that example. A couple more examples for you guys. Oh, maybe just one more example. The double pendulum. So I wouldn't even begin to know how to solve this problem in terms of like freshman mechanics, right? Like you got to write forces and like try to solve, I don't even know. But with our Lagrange method, it's pretty easy. You just got to pick coordinates which describe the problem. So if you've got like one mass and then another mass, and they're connected by, let's see, these are rigid rods, okay, like very light, essentially massless rods that just, you know, stay rigid like that. Then if I measure the angle off the one vertical and the angle off the other vertical, I have completely described the state of the system. So I can use theta 1 and theta 2 as coordinates to describe the double pendulum. I'm going to set y equals to 0 here because I know that potential energy is mgy for a mass that's, you know, I'm assuming this is close to the surface of the Earth. If this is in outer space, who cares? It just sits there, right? So let's assume it's close to the surface of the Earth. So mgy is the potential energy for such a case. And m1, well, look at it. It's L1 cosine theta 1 with a minus. Y2 is minus L1 cosine theta 1 to get to there, and then another minus L2 cosine theta 2 to get to there, down to the bottom, right? So this is the height of mass 1, the height of mass 2. They're both negative because they're under y equal to 0. And then I thought, okay, well, then I'll write down the kinetic energy. And, you know, I was thinking, oh, it's just going to be 1/2 m1, so I can just do L1 squared, theta 1 dot squared. That will give me the kinetic energy of that one. And I think I'm right about that. But then I was like, and then I'll just add 1/2 m2 L2 squared, theta 2 dot squared. And as soon as I wrote that down, I was like, that's too simple. It's got to somehow depend on the fact that m1's also moving. So this one needs a correction. So what I'm writing here isn't quite right yet. minus m1gy1 minus m2gy2. All right, might be wrong. Need to check. Yep, it's missing this term. Let's see why. So if you're wondering, how do you derive such things? Well, you write down equations, if you like, that are based on the trigonometry of the problem. So like here, this is the x coordinate for m2. This is the y coordinate for m2. I just take, sine theta 1 and sine theta 2 because of the, the way it's defined up there, and differentiate those. And then, of course, the speed for m2, it would be x2 dot squared plus y2 dot squared, right? Just because that's the speed in terms of the Cartesian coordinates of m2. And so to get the speed converted into theta 1, theta 2 terms, I just do the calculus and do the algebra. Here it is. Square that thing out, and when you square it, what happens is that you get the cosine squared terms from this one and that one coming to give me this one. The sine squared terms and cosine squared terms from this one and that one give me that. And then the middle terms, I get a 2L1 cosine theta 1 sine theta 2 theta 1 dot theta 2 dot with a minus. And then I get a plus 2 L1 sine theta 1 dot plus times L2 cosine theta 2 dot. Oh no! Oh man! Rats. Those don't cancel, do they? Oh, shnikes. Look at that. Look at that. I just... Yowzers. That's not... Okay, fine. So I get a minus 2 L1, L2, cosine theta 1, sine theta 2. We'll fix it on the fly here. Theta 1 dot, theta 2 dot. From the first, from this one, right? And I'll say plus more. And then plus 2 L1, L2, sine theta 1, cosine theta 2, theta 1 dot, theta 2 dot. Now I think you could combine those, right? You could, oh man, you could put these two together. See, because I've got an L1, rats. So I believe what I could do is just say add minus, this is the kinetic energy, right? So minus, it's from M2, so minus M2, I'd say over 2, but I don't need the over 2 because of the half, right? So, sorry guys, I try not to think too much while I'm making these. All right, minus M2, and I can combine these two because I can use adding angles formula. So I've got like a minus 2 L1, L2, and then let's say sine of, I want to say theta, well I could, hopefully I'll get it right, theta 1 minus theta 2, I think that's what I want, theta 1 minus theta 2, because this minus is on the sine theta 2, so it's like I get sine theta 1 cosine theta 2 minus cosine theta 1 sine theta 2. Yeah, and then of course the theta 1 dot, theta 2 dot terms. Okay, so oopsie. Man. Oh well. So all this stuff here is what I was calling the quote-unquote squiggle squiggle on the line above, right? Whew. So it's worse than I thought. So there's your Lagrangian for the double pendulum. And then I thought I was calculating the Lagrange equations for it. So my partial L, oh phooey, I gotta fix these. Partial L, partial theta 1, see, I thought it would just have this term. Can you see what I'm pointing at? No, you can't. All right, let me get it. All right, so I was thinking when I did this partial L, partial theta 1, I would just pick up the derivative of that going to that, the derivative of this going to that, and I guess that would have been it, right? Now I don't, rats, actually this, so this one's bad. It adds, so, goodness. So partial L, partial theta 1, I have to do what? Add, this would make a good homework problem, wouldn't it? I should just make this homework problem. So correct my Euler-Lagrange equations for the double pendulum. Let's make that a homework problem. I'll do a little bit of it more though. Partial L, partial theta 1. I'm missing my plus, listen to me, minus m2 L1 L2, derivative of sine is cosine, theta 1 minus theta 2, and the in-chain rule gives me a 1. No surprise there, but look at this, I get a theta 1 dot, theta 2 dot, yowzers. That's just the contribution of this guy to the partial L, partial theta 1, right? And then I still have also, so let's say that that's got to go somewhere in here, you know. Here, I'll tell you what, I'll put it back at the front. And then at the end here, I need to also add ddt of what? Probably haven't left myself enough room. Ddt of the partial L, partial theta 1 dot that I've ignored, which would have been, you know, minus m2 L1 L2 sine theta 1 minus theta 2, and then that just leaves me a theta 2 dot, right? So I'm missing two terms in the first Euler-Lagrange equation, and you know, similar error missing a couple terms, right? From the term just discovered mid-lecture. Okay, so I'm going to make fixing the Euler-Lagrange equations part of your homework. That should be a relatively low stakes homework, I hope. It's just, it looks scary, but there's not much going on there, yeah. And then example 5, let's find the, let's think about a free particle with spherical coordinates. So we've got, I'm using spherical coordinates r, theta, phi, and this is the physics sphericals. And so when you differentiate, assuming that r, theta, and phi are functions of time, here's your x dot, y dot, z dot. And when you square these guys and add them together, there's a beautiful bunch of telescoping cosine squared plus sine squared as being 1. Like when you add x dot squared plus y dot squared, you end up with like the sine squared, r dot squared, and then these two kind of combine, and you get r squared cosine squared, and these two combine, so you get, you know, like so you get an r squared sine squared theta, words. You get r squared theta dot squared cosine squared theta, and a r dot squared sine squared theta. Anyway, when you multiply these things out and add them together, it gets you to here. Maybe I should make that a homework. It's not especially exciting, but if you FOIL these things out, a bunch of things cancel and combine, and they end up giving you this. Which means that the Lagrangian for this free particle is just 1/2 m. So what this is here is a formula for the speed squared in physics sphericals. And as such, the Lagrange equations are these. Here's your radial equation, here's your theta equation, and apparently the angular momentum in the phi direction here is conserved. So that's kind of cool. I think that's angular momentum in the phi direction. Because I think, well, it's the angular momentum about the z-axis is what it is, if I remember right. Hopefully. I'd have to draw some pictures, but it might be interesting for the reader to try to draw pictures and understand. Is this, am I right? Is that the angular momentum in the z direction being conserved? I think it is, but anyway, my larger point to you is that this is the same physics as example 1, but look at how much more complicated the equations of motion here look in terms of spherical coordinates, right? So it's interesting, and yet, of course, this is the right way to solve some problems. Did I say this is the last example? I spoke wrong. There's another. Spoke too soon, I should say. So the other example I have for you guys, example 6, you have a particle constrained to a cylinder, r equal to r. Here x is r cosine theta, and y is r sine theta. So I'm using a different theta and r than I did from the previous example. Now I'm kind of using math polars. So the Lagrangian, 1/2 m r dot squared plus r squared theta dot squared, that's the kinetic energy. And then you can throw in what's called a Lagrange multiplier, lambda, and then r minus lambda, r minus r. So this is the constraint, r equal to r. And then because I forgot until the end of this example, it's three-dimensional. So 1/2 m z dot squared, there's the rest of the kinetic energy. So your, xy part becomes r and theta, your z part is right there. And so in this context, there are r, theta, lambda, and z as my variables. So the Lagrange equation for lambda, lambda's sometimes called, I'm trying to remember, I think maybe frozen. It's got no dynamics, right? The equation for it's just algebraic. So this is just a sneaky way of imposing a constraint on other variables by introducing what's called Lagrange multiplier in this context, which doesn't look much like your Lagrange multipliers from other places that you've seen. And then here's the radial equation and the theta equation. Now theta gives you the conservation of angular momentum, mr squared theta dot is conserved. And the radial equation, if you rewrite it, it gives you mr double dot equals to mr theta dot squared plus lambda. So this, as I'm explaining down here, is really just the, centrifugal force, really. I mean, it's this is the mv squared over r term. And so because in this context r dot is 0 and r double dot is 0, we actually get lambda is equal to minus mr theta dot squared, which is minus mv squared, which is to say that it turns out that the Lagrange multiplier is exactly the force needed to impose the constraint. That's kind of cool. That's not an accident either when you study these things. The significance of the multiplier has to do with the force needed to impose the constraint, and that's what happened here, not an accident. And so lambda is exactly the force required to keep m from flying off the cylinder. All right, and this one I can actually solve. So theta dot is equal to L0, the angular momentum, over mr squared. Let's call that omega naught, just to make it simple. So if you integrate this, you get theta is theta naught plus omega naught t. And mz double dot equal to 0 gives you a line in z. And so altogether, going back to Cartesian coordinates, you've got r cosine theta plus r sine theta, comma z, which gives you this parametrically. And then different choices of omega naught or vz will give you different kind of things. Like if you take omega naught equal to 0, you get a fixed you get a fixed angle and you just go up and down the cylinder. So one of the paths here one of the paths that a particle constrained to the cylinder, a free particle constrained to the cylinder, would be a vertical line. On the other hand, if the VZ is equal to 0, you go around a circle on the z equal to z0 slice, and more generally, you're going to get some kind of thing like that. And these, the thing like that, I can illustrate a little bit here. So what's going on is this is actually the equations for like geodesics on a cylinder. So like here's one. So if I draw it like that, then when I take the paper and I just make it into a cylinder, if I was doing it carefully, like same radius circle on top and bottom, like an honest to goodness right circular cylinder, this path that you're looking at here is the geodesic. It's the path of least distance on the cylinder between those 2 points. Now, I put some scare quotes on my geodesic there because a geodesic technically has to be parametrized with respect to arc length, I think. So I don't think that's the case. So I think these are sometimes called like pre-geodesics. Like a pre-geodesic is something that if you reparameterize with respect to arc length, you've got an honest to goodness geodesic. But so anyway, that's the other thing you can use variational calculus for, is to like phrase the problem of finding a geodesic on various surfaces and stuff, or minimal surface. Listen, variational calculus has vast applications, of which you really haven't seen many in your courses, I don't think, because you probably didn't have a course in variational calculus, right? Which is unfortunate for all the time we spend on calculus to not get to that. It is kind of sad, isn't it? But anyway, that's about all I got to tell you about Lagrangian mechanics. So up next, we're doing classical field theory. So thanks, guys.